This presentation provides an overview of Chapter 14 in the book titled Simple G, a gridded economic approach to analysis of sustainability of the Earth's land and water resources, edited by Iman Hakiki and Thomas Hurdle, and published by Springer. This chapter introduces a special version of the Simple G model, and an application of this model for the analysis of nitrogen management policies in the U.S. This slide provides an overview of all chapters in the Simple G book, each of which has an accompanying presentation to motivate the material covered in that chapter. During this presentation, I'll cover Chapter 14, which is on how and why tackling policy leakage and targeting hotspots could be key to addressing the wicked challenge of nutrient pollution from corn production in the United States. Previous chapters laid the groundwork by providing theoretical foundations, introducing general conditions, specifying mathematical equations, discussing the gridded data and parameters, computer implementation, and validation. In this applications chapter, we'll focus on the use of this framework to look at strategies for managing local water quality and the associated spillover effects. Non-point source water pollution in the U.S. is mainly attributed to corn production, which is dependent on nitrogen fertilizer to sustain yields. Various management strategies have been proposed, but quantifying and comparing their effectiveness, especially for large regions, is often beset by data and computational challenges. In this presentation, we show how these hurdles can be navigated by integrating an agronomic and an economic model at fine scale, as well as the merits of doing so. The model created for this study is the Simple G US corn-soy model. It's restricted to 2 crops as a compromise, to accommodate the availability of agroecosystem information that is not provided for every crop. The technical contribution of our method is the creation and use of transfer functions that describe the yield and nitrogen loss responses to nitrogen applications by location and irrigation type. Please refer to Chapter 14 of the book for further details. Using this tailored model, we study 4 nitrogen management policies, both individually and combined, that include nitrogen application rate reduction and splitting nitrogen application, which are nationwide strategies, while controlled drainage and wetland restoration are feasible only for certain locations. We find that none of these policies individually can achieve the hypoxia task force goal set by the EPA. A substantial reduction in pollution, however, can be achieved by implementing them in concert. The effectiveness of each policy varies by location, emphasizing the importance of targeting, in terms of both practice and location selection, to improve the cost-effectiveness of conservation practices. Despite the benefits, a targeting policy could cause unintended consequences by displacing production to non-targeted regions, where nitrogen use efficiency is low, thereby offsetting the achievement of the policy. One possible remedy to this spillover effect is to implement the targeting policy in combination with a nationwide mitigation policy. This slide uses a figure from the chapter to illustrate the market-mediated spatial spillover effect mentioned on the previous slide. When some, but not all farms are targeted, the comparative advantage of farms is altered, and the changes are transmitted by prices in input and output markets across different scales, leading to the displacement of crop production and pollution. We find that the spillover effects depend on the cost burden of conservation on farmers. The higher the farmer's burden is, the larger the ensuing output reduction and subsequently market-mediated spillovers are. Of course, the magnitude of the leakage also varies with the specifics of the policy implementation, including foregone production value, co-payments required of farmers, and adoption rates. Please refer to this chapter for more discussions about the mechanism and the significance of this effect. To conclude, this chapter finds supportive evidence for the effectiveness of implementing combined conservation policies, but also raises a caveat relating to the market-mediated leakage effect, which is discussed more thoroughly in a separate chapter in this book. Another contribution of this application is the way of creating and using transfer functions to integrate economic and agroecosystem models. We see this capacity as one of the key factors to advance the scientific character of interdisciplinary research. If you're interested in this topic, further discussions can be found in the final book chapter on Simple G Future Directions. On this slide, you'll find the link to the Simple G webpage where you can find additional resources, as well as links to the book and other chapter presentations. Lastly, we also gratefully acknowledge support from the U.S. Department of Energy, the Department of Agriculture, and the National Science Foundation. Thank you for watching this presentation on the Simple G book, Chapter 14. We encourage you to explore the other companion videos that accompany the book on the Simple G webpage.